In this video, we're going to introduce the concept of equilibrium, go over different types of systems, and see how we can determine equilibrium law expressions. Okay, so this first page here goes over all of the outcomes that we are going to learn in this unit. Now, starting off with equilibrium, how it gets established is first by starting off with the reactants. So the initial reaction before the products are formed, this is what's happening in this picture here. So we're starting off completely with reactants. No products have formed just yet. Okay, and each one of these circles represents the moles of reactants. Okay. So on the left-hand side of all of these diagrams represents reactants. Each circle is a mole of substance. So when they're on the left-hand side, it represents the moles of reactants. When it's on the right-hand side, it's going to represent the moles of products. Okay, so starting off, we have 100% reactants and no products. Okay, then the forward reaction happens and it forms the products. Now what happens after the forward reaction has happened? Now this system is going to start getting towards equilibrium, or start moving towards equilibrium, and how that gets achieved is through the reverse reaction happening. So now what's happening is we went from having a lot of products, and now that the reverse reaction is happening, okay, we're reforming reactants here. Okay, and as these forward and reverse reactions eventually reach the same rate. So what I mean by that is the forward rate of reaction is equal to the reverse rate of reaction. That establishes something called dynamic equilibrium. Okay, so it does say to note the number of moles on the reactant and product side. So a common misconception is that equilibrium must mean that there's an equal amount of moles of reactants and products. That's not the case. That's not what equilibrium means. Okay, dynamic equilibrium means that your forward rate of reaction and your reverse rate of reaction are the same. Okay, so we'll go over dynamic equilibrium again on the next page and exactly what that means. But in the meantime, we're going to go over chemical systems. So there's a few assumptions that we're going to make about chemical systems. So we're going to assume that all reactions are going to occur quickly, that they're all spontaneous, and that they are all quantitative, so they go to 100% products, and there's no limiting reactants left, and all reactions are stoichiometric. So that means that we can predict the amount of products since they go to completion. However, the problem is that all of these assumptions, they don't necessarily happen in real life. So many chemical reactions don't necessarily go to completion. Okay, and that's because something called dynamic equilibrium exists. Okay, so the different types of systems that you're going to want to be aware of are open systems, closed systems, and isolated systems. So we'll put those definitions up here. So an open system is a system in which matter and energy can be exchanged. So if I was to give an example of what an open system is, really a system can be anything, but in the context of chemistry, we often end up talking about reactions. But what I'm going to do is I'm going to give more kind of real life examples here, just to make the definition a little bit more relatable here. So an example of an open system could be like a room with its door open. Okay, so people can go in and out of the room. The room can get warmed up or cooled down. That's just cases of matter and energy being exchanged between the room and the surroundings. So the room is considered the system, whereas everything outside of that room is considered the surroundings. The next system is a closed system. So where a closed system is different from an open system is that no matter can be exchanged, but energy can go in and out of the system. So an example of a closed system would be something like a battery, right? You can't put any matter into a battery. However, the battery can be used to charge something, or if it's a rechargeable battery, you can put it into the battery charger and energy can go back into the battery. So a battery, or could use a space heater as a closed system. So you can't put anything inside of a space heater. However, it can give off heat and heat up its surroundings, right? Or the surroundings could cool down the space heater once it gets turned off. Another example could be your phone. Right? You're not going to exchange matter between like yourself and the phone. However, the phone can give off like light energy or heat energy, so on and so forth, just with energy. Now with the last system, that's an isolated system. So this is a system where no matter is going to be exchanged and no energy can be exchanged with the surroundings. So with this, it's a little bit hard to come up with examples. But one example could be the universe. Right? No external matter outside of the universe or energy outside of the universe is going in, okay, in or out. Okay, so those are the different types of chemical systems. We do have these assumptions, but like I said, many chemical reactions, even though we typically assume that they go to 100% completion and therefore are stoichiometric, many reactions don't do that in reality, and they actually exist at this state of dynamic equilibrium. So dynamic equilibrium, that is a term that you're going to want to know. And we'll define it a bit more on the next page here. But just to break this word down here, dynamic, that means active or changing. And equilibrium, that just means balanced. Now, once again, equilibrium, even though we're saying it means something like balanced, remember that equilibrium does not necessarily mean that you have equal amounts of reactants and products. So a system that's at dynamic equilibrium it's not going to look like there's much happening if you're just staring at a beaker where you have some sort of reaction that's at equilibrium. You're not going to see any changes. But that's because you can't see what's happening at a microscopic level. You can't see that the products are forming or the reactants are reforming. You can't see that forward and reverse reaction happening just because you can't see what's going on at the microscopic level. So a system at dynamic equilibrium, it's going to look like nothing's happening. So nothing's happening, but this is because you can't see what is happening at the microscopic or molecular level. So with talking about the fact that you can't see what's happening at the microscopic level, let's talk about microscopic properties of dynamic equilibrium versus macroscopic. Okay, so microscopic, micro means that we are focusing on small stuff. Okay, so this is what you won't be able to see with your eyes. Now, macroscopic, macro means big. So those are going to be what you can see. So for the microscopic properties, those are going to be continually changing, and at the molecular level, there is a great deal of change. There's the forward reaction happening at dynamic equilibrium at the same rate as the backwards reaction. Now, with the macroscopic properties of a system at dynamic equilibrium, those are going to remain constant. So some examples of macroscopic properties, those are going to be something like temperature, color, pH. Those you can see. Okay, so with temperature and pH, obviously for temperature you'd need a thermometer to be able to see that, and with pH you'd need a pH meter to see that, but you don't need to zoom into the molecular level to see that, whereas with microscopic properties we're talking about products forming, reactants reforming, that sort of thing. Okay, so very important that you know what dynamic equilibrium is. What it is the balance between the forward and reverse reactions. And the forward and reverse reactions, they are occurring at the same rate, and that's why the observable or the macroscopic properties are going to remain constant. Now, how we show dynamic equilibrium in a chemical reaction, you can use one of three different ways to draw the arrows. So you can draw the arrows either like that, so one forward, one reverse arrow, or a different way to do the same thing would be like that, or you could draw the arrows like that. So all of these three different types of drawings, they all represent dynamic equilibrium. I tend to use this representation a lot more, but you can choose which one of these to draw when you are trying to represent a reaction or a system at dynamic equilibrium there. Okay, so for example, we have this equilibrium equation. Okay, so we have sodium sulfate reacts with calcium chloride and produces sodium chloride and calcium sulfate. Since this is at equilibrium, I'll draw my equilibrium arrows. So collision theory explains that the reverse reaction can occur. So what that's going to entail is that the products can react to reform the initial reactants that you started with. And the final state of the reaction is a competition between the forward and reverse reactions, and that's why they're occurring at the same rate once dynamic equilibrium is reached. Before dynamic equilibrium is reached, one reaction will be favored over the other, right? Just as it kind of settles down into that dynamic equilibrium. So some important parts to know about dynamic equilibrium. A system at dynamic equilibrium, your concentration of reactants and products, so just know that these like square arrows or these square brackets, they mean concentration of and then whatever's inside those brackets. So square brackets mean concentration of. So your concentration of reactants and products won't change once equilibrium is reached, even though the forward and reverse reactions are happening simultaneously. The macroscopic properties, or the properties that you can actually see with your eyes, they are going to remain constant. But a great deal of change at the microscopic level is going to happen. Now, there are some requirements for a system to remain at equilibrium. The temperature must be held constant. So if the temperature changes, that means your equilibrium constant will change. So that what that means is either the forward or reverse reaction will be favored if your equilibrium constant changes. It's effectively just a measure of which reaction is being favored. And the other requirement is that the system must remain closed for it to stay at dynamic equilibrium. So both physical and chemical changes can reach equilibrium, and we're going to go through 3 examples of types of equilibrium situations. So for the first one, that's going to be solubility equilibrium. So that's where you have a saturated solution with excess solid. So just as a reminder, saturated, what that means, or a saturated solution, that's a solution that can't dissolve any more solid. So, for example, let's say we have a saturated salt water solution that's at some particular temperature. Okay, so we have our reactants being solid sodium chloride, which is salt, that's placed in water, and what that causes is the dissociation of sodium chloride. So we get the ions, the cation and the anion, sodium 1+ and chloride ions. So the forward reaction here, we're going from our crystals to a dissolved substance, whereas the backwards reaction, right, we're going from the dissolved substance to the crystals. Okay, so the forward reaction, so I'm just going to abbreviate forward as FWD, right? That would be the dissolving process. Whereas the reverse, that would be recrystallization. Okay, so we're going from the ions to the crystals. Okay, now one thing I should do, we should make a note. I did say this, I just didn't write it down. So K, that's called the equilibrium constant. And what it does is it just represents conditions. Okay, so it represents the amount of products compared to reactants. So if you have more products than reactants, then that's telling you that the forward reaction is being favored. Whereas if you have more reactants, then that's telling you that the reverse reaction is being favored. Okay, so with our solubility equilibrium, what remains constant? That's going to be temperature, concentration of our ions, mass of sodium chloride. However, the shape of the crystals, so that's going to be a microscopic property that you're not going to be able to see. The shape of the crystals is going to be constantly changing. Another example of an equilibrium situation would be phase or state equilibrium. So for example, we have a mixture of ice and water at 0 degrees Celsius. So the forward process, that would be melting, because we're going from solid water to liquid water. So ice to liquid water. Whereas the reverse reaction, that would be freezing, because we're going from liquid water back into ice. So again, what will remain constant is temperature, and then also water volume, mass of the ice. However, the shape of the ice will be changing there. Okay, our last example of a system at equilibrium will be chemical reactions that occur at a constant temperature. Okay, so for example, we have nitrogen monoxide reacting with oxygen gas to produce nitrogen dioxide. So what's remaining constant here is temperature and pressure. Another example would be carbonated beverages. So with carbonated beverages, because we have carbon dioxide, that's what the gas is that makes drinks like pop fizzy. And what happens is that carbon dioxide reacts with water to create carbonic acid, right? But there's this equilibrium that occurs within your pop can, right, where we have carbon dioxide reacting with water to produce carbonic acid, but then I guess for this, how this is written, it'd be the forward reaction, right? The products get formed from the carbonic acid, so carbonic acid breaks down into water and carbon dioxide. So what we just talked about, these three situations here, all of them are examples of a dynamic equilibrium, which is going to mean that there's a balance between that forward and reverse process. Okay, so again, for dynamic equilibrium, it's very important that you understand that what that means is that the forward and reverse reactions are happening at the same rate. So with dynamic equilibrium, there's a couple of different expressions here. We have homogeneous expression, which means everything's in the same state. So the first example for the chemical reactions, notice how everything is a gas. That would be a homogeneous expression. Okay, whereas a heterogeneous expression would mean that there are substances in different states. So the second example here would relate to that. So we've got carbonic acid as an aqueous substance, water as a liquid, and then carbon dioxide as a gas. Everything is in a different state. Now, moving on to equilibrium law expressions. So this is what gives us our equilibrium constant. So an equilibrium law expression constant is the product of the molar concentrations of products for a chemical reaction. Okay, so that's important that you know what this is. Okay, and each of them are raised to the power of its respective coefficient in the equation, and we are assuming that the chemical equation is balanced. Okay, and if it's not balanced, then you need to balance it before you write your equilibrium law expression. Then the products are going to be divided by the product of the molar concentrations of the reactants, each raised to the power of its respective coefficient in the equation. So there's some rules for equilibrium law expressions. Concentration, always going to be in moles per liter. Product concentrations are always going to be in the numerator of the equilibrium law expression. reactant concentrations are always going to be in the denominator. And the powers to which concentrations are raised is always going to be determined by the coefficients in the balanced chemical equation. So if you wanted a template for what this looks like, so I'm just using a general template to represent a system at equilibrium. So this little a is going to be the coefficient for substance A, plus this little b is the coefficient for substance B. And then at equilibrium, little c is the coefficient for substance big C, and then little d for substance D. So how we would write this equilibrium law expression is we would go the equilibrium constant is equal to, I like to start off with products divided by reactants just to help me kind of figure out where everything goes. And then I'm going to start over here. So the concentration of substance C. So to differentiate the two, because it might get a little bit confusing when I'm writing the equilibrium law expression, I'm going to put a line over top of the little c just to help differentiate the two. So it's raised to the power of little c. And then we're multiplying it by the concentration of substance D raised to the power of coefficient D. Then for the reactants, that would be substance A raised to coefficient A times by the concentration of substance B raised to the coefficient B. So that is a template that you can use to write equilibrium law expressions. All right. So how do we actually do this? Let's use some numbers here. So the following reactions occur in a 500 milliliter container. So we've got this reaction here. So we've got ethine reacting with oxygen. So basically we have a fuel burning in the presence of oxygen and it produces carbon dioxide and water vapor. So at equilibrium, so it's super important that you take equilibrium values to create an equilibrium law expression. There's 0.7 moles of ethine and 0.8 moles of oxygen, 0.9 moles of carbon dioxide, 0.5 moles of water vapor in a sealed 500 milliliter container. We need to write out the equilibrium law expression and then determine the equilibrium constant, Kc. Okay, so I'm going to write out what I just said. To figure out the equilibrium, so extra emphasis on equilibrium here. To figure out the equilibrium constant, you must use concentration at equilibrium. All right, so let's write out this reaction. I'm going to write it out again just so I can use it to organize my information. Okay, so we've been given a few different pieces of information here. So we've been given moles of each substance, so I'm representing moles with N. So for ethyne, that was 0.70. And what I'm going to do, actually, I'm going to write this over here and then write my units so I'm not writing them every single time. We've got 0.8 of oxygen, 0.9 for carbon dioxide, and 0.5 for water vapor. Now they told us the volume, so that's important as well. But what I'm going to do is I'm going to represent volume in liters instead of milliliters. Okay, so how you convert from milliliters to liters is you divide by 1,000. So that's going to be 0.5 liters. Okay, and that's going to be the case for all of these substances because they're all in the same container. So remember that we want to use concentration, and you got to remember that concentration is equal to moles divided by volume. Okay, so our units are going to be moles per liter. So what I'm going to do is I'm going to take 0.7 and divide it by 0.5. So I get 1.4. So that's 1.4 moles per liter. So then 0.8 divided by 0.5, that's going to give me 1.6. 0.9 divided by 0.5 is 1.8. Now just keep in mind with SIGDIGs, since these aren't final answers, we don't need to worry about SIGDIGs right now. So 0.5 divided by 0.5, that's just going to give us 1. Alright, so now that we have all of our concentrations, we can actually get to writing the equilibrium law expression. So Kc, again, I always like starting off with products divided by reactants. Okay, and I'm going to color code these so it's easy to follow here. So again, starting off with the products, we have carbon dioxide raised to the coefficient, so that's 4 for carbon dioxide. And then we have water. So you don't have to write states for the equilibrium law expression, but you do have to write states when you're writing chemical reactions. So I'm going to raise it to the power 2 because that's a coefficient for water vapor divided by ethyne raised to the coefficient, which is 2, and then oxygen raised to the power of 5 because that's the coefficient. Okay, so now that we've figured out where the concentration of each substance goes, we can plug in our numbers here. Okay, so for carbon dioxide, that was a concentration of 1.8 raised to the power of 4 times by 1 for water vapor raised to the power of 2 divided by 1.4 raised to the power of 2 times by 1.6 to the power of 5. Alright, so let's put this into our calculator here. I'm going to put everything in the numerator in brackets and then everything in the denominator in brackets. So 1.8 to the power of 4 times by 1. You could write 1 to the power of 2, but 1 to the power of 2 is still 1. Divided by 1.4 to the power of 2 times by, don't need that bracket, 1.6 to the power of 5. Hit enter and we get 0.5107, goes on forever. All right, now with your equilibrium constant, there are no units because concentration cancels out completely, or our units for concentration cancel out completely. So no units for your equilibrium constant. All right, but we do need to take into account sig digs, and all of our given numbers, or most of them, have 2 significant digits. So a reminder here that leading zeros, or zeros that come in front of non-zero digits, those are not significant. Any digit that is not 0 will be significant, and any 0 after non-zero digit, so trailing zeros, those will be significant. So all of these first 4 values, they all have 2 significant digits. This one has 3. You always go with the lower amount of sig digs. So our answer needs to be in 2 sig digs. So I'm going to round that off. There's my cutoff line here. So our equilibrium constant is 0.51. So this is the equilibrium constant specifically for this reaction here. Okay, so we will get into, okay, what does this equilibrium constant value mean? But right now, all that matters is that you know how to calculate, how to, first of all, set up your equilibrium law expression, and then also how to know how to determine or calculate your equilibrium constant. So for equilibrium law expressions, like, by the way, if a question asks you for an equilibrium law expression, this would be, for this question, this would be the equilibrium law expression. Okay? But there are some rules as to what you can include in your equilibrium law expression. So what's always included is going to be your gases and aqueous solutions. What's never included is solids. And the reason why they're never included is because you can't find the concentration of a solid. And what's sometimes included would be liquid. So the rule is if you have more than one liquid in the equilibrium equation, then you include all of the liquids in the expression. Okay, or in the equilibrium law expression. However, if you only have one liquid in the equilibrium equation, you do not include it in the equilibrium law expression. Okay, so let's say, for example, just to kind of go over these rules here, let's say you have sodium sulfate. Oh, don't need those brackets. So sodium sulfate, aqueous, and you have calcium nitrate, aqueous, and it's in equilibrium with sodium nitrate, aqueous, and calcium sulfate, which is insoluble. Okay, so if you were trying to make an equilibrium law expression out of this, you would not include calcium sulfate because it's a solid, but you would include the sodium sulfate, calcium nitrate, and sodium nitrate because they're all aqueous. So don't include because it is a solid. So solids do not get included in your equilibrium law expression. Okay, let's do another example here. So let's say we had H2S aqueous plus water as a liquid is in equilibrium with a hydrosulfide anion or a hydrosulfide ion plus hydronium. All right, so if we were to create an equilibrium law expression from this equilibrium reaction or this reaction at equilibrium, we would not include water here because we only have one liquid. This is the only one, so because there's only one liquid, it doesn't get included. So don't include because, actually I should say don't include in the equilibrium law expression because it's the only liquid. If you are asked to figure out the equilibrium constant for the reverse reaction, all you need to do is take the reciprocal of the forward reaction. Okay, so we'll write that out and then I'll show you what I mean. So we have the equilibrium constant for the forward reaction. So just keep in mind here what I'm doing is I'm using the template that I wrote out here. So my products are substance C and D. My reactants are substance A and B. So remember for the forward reaction, it's always products divided by reactants. So we have substance C raised to power of coefficient C multiplied by substance D raised to coefficient D. Substance A raised to power coefficient A. Substance B raised to the power of coefficient B. Now, what that would look like for the equilibrium law expression for the reverse reaction. So we'll say reverse, actually, I'll write that out. For the reverse, it would be reactants over products. Okay, so again, you're just taking what we had over here and you're just flipping it. So what was in the denominator now goes in the numerator. What was in the numerator will go down into the denominator. So if you wanted to see what this looks like with numbers, let's say for the equilibrium constant for the forward reaction, let's say that's equal to 20. If you were asked to find the equilibrium constant for the reverse of that exact same reaction, you would just take this number and flip it. So we would go 1 over 20. Right, so 1 divided by 20, that's going to give us 0.05, and we're not going to include any units. And I'm going to make sure we'll put this in the same sig digs here. Okay, so keep that in mind. You do need to know how to write equilibrium law expressions. You do need to be able to calculate equilibrium law constants, and you need to be able to do all of that for both forward and reverse reactions. So make sure to pay special attention to these rules as to what can be included in your equilibrium law expression and what can't.